All right. Yeah. Okay, I guess we can start slowly. Um, so today's, the last lecture of the third week. We are on lecture number 9, and we continue talking about, minimizers of the action functionals. And in particular, I mean, some of the points today I have already talked about it, but I want to emphasize things again so that we have a more systematic pictures of everything. I mean, for the today, the goal is going to be essentially 2 points. So the goals for today is, sort of re-emphasizing about the connection between the Lagrangian and Hamiltonian viewpoint. And later on, we're gonna go back and forth a lot between the two. So I mean, it's good to keep reminding us. Um, the second goal, which is a major goal that I wouldn't be able to finish it today, but we're gonna discuss some points about it, and then we're gonna finish it next time, I hope. Is that we're gonna try to show, I mean, this the second one is a major goal, is that if say gamma in curly A, which is just a set of absolutely continuous curve, uh, you know let's let okay, maybe let me write this way so that it's easier to write. So if gamma is absolutely continuous, uh, is a minimizer, then we can show that actually gamma is ck, and gamma satisfy the Euler Lagrange equations. So the second one is a major goal because it turns out that we go from the most general setting, but still we can prove that any minimizer is ck, and then it satisfy Euler Lagrange equations. And this one by no means is simple, and we're gonna also need to use certain results to do that. I'll mention, like today we're gonna need to use one result without reproving it. Anyhow, that's the goal. So let's start, and then again, I'm mentioning again some points, so bear with me. So L is ck, and whenever I need to put more assumptions, I put more assumptions like L, dx, L, and dvl are bounded uniformly continuous and Lipschitz, when V is bounded. So things are nice. L is superlinear and uniform, locally uniformly convex. So I would say that, I can say that L is ck, nice, superlinear, and locally uniformly convex. So I mean that those are the keywords that we can take into account. And later on, we're going to work on the torus only, so everything should be fine. And again, I recall what we did. We are concerned with the minimizing problem, and the point is that depending on what, let me mention here that it really depends on what is the admissible set. Okay. The admissible set can be rather restrictive. It can be like, seek two functions, or it can be, like piecewise C1. So in this case, if the admissible set is the set of piecewise C1 curves, continuous piecewise C1 curve, then we already proved that gamma is ck and gamma satisfy the Euler Lagrange equation. So that's what we already proved. Okay, so although we have discussed about this, I want to have again a systematic viewpoint about switching between back and forth between Lagrangian and Hamiltonian viewpoint, and we're going to prove something more today. Here is that again you have that okay, if gamma is continuous, piecewise C1 extremer or minimizer curve, then you have that gamma is ck and gamma satisfy the Euler Lagrange, right? And the Euler Lagrange is always like d over dt because the v variable is what you differentiate. You have gamma dot. So I mean you have one more derivative. That's why you have d over dt. This is dx, L of gamma dot. Okay. And as always, we record this variable. We name it p. So pt. This variable. This one is called the generalized momentum. I mean, in classical mechanics, P is exactly mv, which is the momentum. But in Lagrangian mechanics, then this comes with like a generalized momentum. At least that's my understanding of the notions. There can be different notions, and then we define x and p. Again, x is then stands for just gamma t. This is just the position of your particle. And then pt is exactly the generalized momentum. And then we go with this one. The one of the key point about the duality here is about the dual between Lagrangian and Hamiltonian, right? So we talked about this already, but let me recall it. So if you have pt is dv of L gamma t gamma dot t. Again, I mean, pause me if you want to discuss or ask questions. Um, so if pt is this one, then p is a dual variable of this gamma dot, right? I mean, that's between p and v. So then you can surely have that gamma dot of t is nothing but dph of gamma t pt. And because you have gamma is nothing but x, so you can also write as dph of xt pt. Okay. So that's the two thing. And also because you have, again, that's the duality between gamma dot and p. Then and also then you also have that you have the box here. So you have p dot with gamma equals to L of gamma dot plus h of xp. Again, I mean, x is gamma, so I can write that way. So you see that the duality plays a lot of role here. And you can see that from here we have exactly the Hamiltonian system, right? We highlighted it here because x dot is gamma dot and gamma dot is dph. It's exactly that, right? And then p dot, p dot is coming from, again, p dot is coming really from the Euler Lagrange equation. So p dot t is nothing but d over dt of dv L gamma t gamma dot t. Okay, and this is nothing but dx of L gamma t gamma dot t. And then by the duality that we proved earlier, dxl is equal to minus dxh of xt pt. Okay. So that allows us to come up with this Hamiltonian ODE. X dot equals to dp and p dot equals to minus dx h. And eventually, by the end of today, we're also going to talk about methods of characteristics. And surprisingly, we also encounter Hamiltonian ODE. So, it comes from various aspects. And as I said, this one is truly coming from it's truly the key points of, so this is the key object for Hamiltonian ODEs, Hamiltonian dynamics, and also symplectic geometry. Okay. And I believe that 2 or 3 years ago, Sergey Bolotin taught exactly this course, but it's really more on classical KAM. And I mean, I was sitting in his class for sure, and I mean, not all the times, but certain portion of the class, and he started with this one. And one of the key point of this Hamiltonian system is that you have the conservation of energy. So let me say that this is one of the most important point. It's the simplest one, but this is uh, saying that we have conservation of energy along the uh, the the parts xtpt. Okay. And in fact, this is actually also the key point of symplectic geometry, because what I'm doing the computations here, and again, let's say that we know nothing, we just differentiate the Hamiltonian in xtpt, and here we need to use chain rule and product rule, whatever, right? If you differentiate in x, then you have xt coming out, so you have x dot t, right? If you differentiate in p, then you would have p dot t coming out. And here you see that x dot is dp, and p dot is dx minus dx, right? So when you combine together, you have exactly dx h dot with dp h minus the same thing, so it's 0. So we have conservation of energy. It's very, very simple. But nevertheless, sometimes in the literature, when so in terms of notion, in the literature, sometimes you can see people write something like h of phi. This is the Poisson bracket. Again, the sign plus or minus doesn't matter. It's dph dot with dx phi minus dxh dot with dp phi. And they say that this Hamiltonian system is integrable if you can find n independently and linearly independent functions phi, so that you have the Poisson bracket h phi is 0, because whenever you have a Poisson bracket is 0, that means that like you are on the energy level of that functions. Okay, maybe let me make a remark. So a remark here is that if h phi, the Poisson bracket is 0, then you actually would also have that t maps to phi of xt pt is constant. Okay. All right. So that is an important remark, because what does it tells us? Okay. So I mean, the problem here again, for mathematicians, integrability is a very vague notion. What it says is essentially we have a system that is solvable, and mathematical terms for solvable is very different from engineering terms for solvability. Solvability for us is sort of something that uh, sort of really solvable. So what we are seeing here is that we have a system of 2n variables xtpt. Okay. Right, because each of that is n variable, x is n variable, and p is n variable. So if we have h of xtpt is constant, say equals to c constant, then assuming that h is very nice, this allows us to reduce that xtpt is staying on a manifold of 2n minus 1 dimension, right? So eventually, if the problem allows you to have many such phi in such a way that, okay, so if there exists, say, phi 1, phi 2, up to phi n minus 1, linearly independence, or I mean, this is also a vector, so that the Poisson bracket of h and phi I is 0, then you also have that not only h of xt pt equals to 0, but also that phi I of xt pt equals to 0 for all I between 1 and n minus 1. And this essentially allows you to reduce the problem to, after taking the intersections of all such manifolds, or you can think that you have two n variables and you have a system of n sort of linearly independent, whatever that means, equations, and the problem allows you to reduce the problem this to um, just solving uh, uh, you know uh, let's say for n unknowns. Okay, and this is called integrable system. Okay, so that's a vector, but anyway, I'm just sort of telling you that's a very classical viewpoint, and in general this is quite hard. It's most of the time not possible to find such a phi so that you have put Poisson bracket is 0, but this is a very useful notions for solvability. Let me know if you have any question. Okay, but we are not aiming into that sort of like classical viewpoint. We're gonna do something a little bit more modern in this aspect. Okay, however, I'm telling you a lot of like stories there, but however, one of the key point that we gain in doing this is that is that at least from the conservation of energy, this allows us to conclude that we actually have that xt pt is uniquely defined given initial data. And this is already important. Okay, why is it important? Because a priori knowledge about h is that it grows up, right? It's super linear, it grows up, and then we don't have any control about whether it's Lipschitz or not and stuff like that, or dph. And again, if you look at into this Hamiltonian system, so we don't know if dph and dx of h are Lipschitz or not in in p, right? Lipschitz or not in p. In fact, if you take h is the classical mechanics Hamiltonian, 1/2 p squared plus v of x, then it's not uniformly Lipschitz, right? Because it's a quadratic term in p. So for the ODE theory, I'm not sure if this Hamiltonian ODE, this star, whether it's has a unique solution or not. Nevertheless, given the conservation of energy, we are good to go. Why so? Because if you have conservation of energy, that means that if you're given initial data, x naught, p naught, then a priori knowledge gives us that h of xt pt equals to h of x0 p0, which is, a constant, right? So it's less than a constant, whatever the constant you chose. Then by the superlinearity of h in the p variable, then you can gain the a priori knowledge is that the momentum or generalized momentum pt is always bounded. Okay, and when it's bounded, by the assumption we put, or whatever, that it's Lipschitz when p is bounded, then you can imply by the classical ODE theory that XTPT is defined for all t. So, so I would say here that a priori knowledge give us the Lipschitz vector field and give us the well-posedness of ODE. I mean, by well-posedness of ODE here, I just meant that the Hamiltonian ODE is well-defined and you have a unique sort of solutions to your Hamiltonian ODEs. Okay. Any concern about this? All right. So if not, then let me move on to the next point. So the next point is that you can see that you can go back and forth between Lagrangian flows and Hamiltonian flows. And this is also very important because, if you want to do minimizing something, then doing it the Lagrangian viewpoint is better. And later on, you're going to see that we're going to deal with Hamilton-Jacobi equations. Then often the case that, it might be like more natural to start with the Hamiltonian viewpoint, the Hamiltonian ODE. So it's really important to be able to go between one of the two, and it turns out that it's exactly the case. So setting the framework, laying down the framework here is going to be really helpful for us later. I mean, you don't have to, memorize all those sort of L and L inverse and stuff like that. But the key is that, we see that we can go back and forth. And I put it here so that, we have a reference later on to go back. So if you go in the Lagrangian flow, you start with a point X and the initial velocity V, right? And you go with the Lagrangian flow. By the Lagrangian flow here, maybe let me make it clear. I mean that you solve the ODE that d over dt of dvl gamma dot t equals to dxl of gamma dot t for t in R, any real number, and you start with gamma 0 equals to x, gamma dot 0 equals to v. So that would be your Lagrangian flow, that you start with a given location and given velocity and you go with the flow. So that's the Lagrangian viewpoint. And the Hamiltonian viewpoint is that you solve the Hamiltonian system, right? So you solve the Hamiltonian system, XTPT, and with given velocity and moment, so given position and momentum, XP. Okay, so let me highlight it a different way. So this is with given velocity and given momentum. So same X, and you see that we have already seen that the map L mapping from XV to XdV of LXV is a CK minus 1 diffeomorphism. Hence, to go, okay. So let me write down here. So you have the map L, it's mapping from XV to XdVL of XV. It's a CK minus 1 diffeomorphism, and you can think of dV of LXV is exactly P, right? So that allows you to go exactly between XV and XP. And that is exactly the case here, you see, So if you want to run the Hamiltonian flow, so Hamiltonian flow, that you run it, this is Vt of H XP, right? So you want to run it. So how, how do you really try to run it otherwise? So the first thing that you want to do is that you want to transform xp back to xv to run the Lagrangian flow, right? So what you would do is that, let's see if I write that correctly. What you should do is that first you take the L inverse of xp. Okay, L inverse of xp gives you exactly back to xv, right? Because this is L, and the other one is going to be L inverse. Um, so you take L inverse of xp to get back to xv, and when you run xv, you would take VTL of xv, and that's the Lagrangian flow. So when you run the Lagrangian flow, you have gamma gamma dot, and from the gamma gamma dot, if you take the L, uh, compose it, that you have xp again. So that's L. So by the way, I'm not a dynamical person, so sometimes I would be a little bit confused between pull back and push forward. So I try to ignore saying that, because okay, that my honest point, because otherwise I would mess it up, between pull back and push forward. This is exactly that, but
Could I ask a question about this?
yes.
So I guess I'm a little confused about the meaning of these mappings phi.
Mhm.
So they input x and v from Rn cross Rn, right?
Yes.
And I guess what are they outputting? So like it says like gamma and gamma dot, but given an x and v,
Mm-hmm.
how do we know what gamma and gamma dot are?
Okay, so good. So you from xv, you map to dvl of xv. Okay. So what is the L inverse, right? That's a very solid question. So the L inverse is that you go from xp. Again, think of p as dv of L. Okay. I'll write down. If you take L inverse, it's gonna give you x and nothing but dp of x hp. Okay. So I mean, so the question is very good, because hidden here is that we are using the duality, is that if you have p is dv of lxv, this is equivalent to the fact that I have p is v. I'm sorry. So v is dph of xp. So this is the hidden point here that allows me to go between the Lagrangian and Hamiltonian viewpoint, because if you look here, let's go back. Um, so what is the P? PT is dVL of gamma gamma dot, right? And vice versa, gamma dot is dP of XP. So so if my starting point is exactly that, if my starting point is exactly uh, p is dvl and v is dph, then when I run the Hamiltonian or Lagrangian flow, this is exactly the you know the the um, the so when I run my Hamiltonian flow, I should have exactly the pt is dvl of gamma t gamma dot t, and vice versa, that I have that exactly gamma dot t is dph, gamma t is just xt, so xt pt. Okay.
I see. So for a given t though, like so these mappings phi, they map Rn cross Rn. They're not mapping functions, right? They're mapping numbers to other numbers.
Oh, okay, so good point. So so what's the function phi, right? So the function phi is that okay, maybe let me draw a picture here. So what's the function phi, right? So phi t of h, they are mapping from a vector in, okay, so it maps from xp to xtpt. So it's a mapping from r2n to r2n. You take a point, so you can, this is essentially point carrier map. So I mean, so okay, so you start with a point. Okay, I don't know how to draw 2D. Uh, uh, so if I'm in 2D, so let's say that you have xp is in R2, okay, So those are the given initial data to you. You run the Hamiltonian flow. This is VTH. If you stop at time t, this gives you XTPT. So the map VH of t is that, you just choose any given initial data, you let it run for a fixed time t, you record what's the endpoint at time t. So that's called the Poincare map. So let's say that, for example, I go with time 1, I start with this panel, I stop at this panel, I take a point here, it somehow end up with this point in the panel, and I keep recording, you know.
I see.
So yeah, so that
Okay.
that's a very good question. I remember I read this one in a very good sign books. I forgot, but I mean, the origin of Poincare map was that it would to not only deal with continuous but also discrete dynamical system. What you can think of is that, like you can see that the orbits, of certain planets, you know they are actually not periodic. Like any planet around the in the solar system. So, for example, the Earth, after a year, it comes back. It's not exactly to the point, but if you take this map, you consider after every 1 year, it comes back to something here on this plan that you're taking sort of the snapshot. And every year, you're going to have a map here that recording the location of the Earth after 1 year, 2 year, 3 years, and it's going to be, dot, 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 dot somewhere in here, and it's nearly periodic. It's not periodic. So this map VT is exactly that. So you can think of T as something fixed, and you keep recording, like, for different input, what's the output? For different input, what's the output? That's that.
I see. Okay. Thank you.
Yeah. Okay. Thanks for the question. So I mean so that's really the map. So it's, I should have mentioned it. Oh, I did write that. Yeah, I didn't mention it clearly, but it's really a map from R2N to R2N. Given initial data, it answered something, and given initial data, it answered something. Um, and this is a very important property. I mean, although it's quite obvious uh, to dynamical people. Again, I vividly remember that Sergei Bolotin also wrote this one down a few years ago. And he has a nice way to say it about pull back and push forward. Anyway, but my point is, it's simpler. My point is that, we are allowed to go between either Hamiltonian or dynamic or Lagrangian framework, and we are free to do so no matter what. And this is very important later on for us. Okay. Um, but I'll recall it whenever we need it. Okay. So that's the first viewpoint. So there were two new things about, first, about the conservation of energy allows us to have well-posedness of the ODE, and the second point is about this neat identity. Okay. And also this way of considering VT and VTL and VTH is very nice, because if you do discrete dynamical system, then it works nicely. You wouldn't have to, like, do it for the continuous one. Okay. Now let's focus on the second point. And as I said, I am not gonna finish this today, because this is really lengthy, and I would, need to see what's the point. Um, and I'll check if I can finish it next Monday. Um, so the assumption is that, now we consider the regularity of minimizers in this absolutely continuous curves. So the admissible set is just this simpler setting, and this is kind of the optimal one, right? This is the sort of like the best case scenario for us to consider what's the admissible set. Um, and we fix the two endpoints of the curves. Again, our picture is always like we fix y here and z here, and we consider all the curves of length b minus a connecting the two. I mean, length here is not exactly the length, but gamma from AB to that. So this is a big theorem. that if we assume L, so the regularity and condition on L, and let gamma be a minimizer, then gamma is Ck and it satisfies the Euler Lagrange equation. It's really a big theorem. Um, and we're gonna prove in the most general setting. And as I told you, there are various very neat and borderline situations in which that the regularity might go wrong. So we really need like L is in Ck. We need like superlinear. We need locally uniformly convex and stuff like that. Um, so here's the result that I need to use. I will tell you what's the deal here. Uh, and what I'm writing down here is sort of literally correct, not absolutely correct, but I don't want us to be clouded with technicalities. Uh, so let me say it first, and then I'll tell you a little bit about the details, and then we go with that. So this is a very important ingredient. So you see, this is one of the reasons why this is a big theorem. We need to use a lot of results, and I would say that this is by no means obvious that this one is written down in many texts. It's written down in Fatih's book and some lecture notes of Hitoshi Ishii or some others that I knew of. But I wouldn't say that this was written down anywhere, in the far past, like in the 80s or something. So it's only written down in 2000s or something. Although, I mean, I would say that the ingredients are there. Okay, so this is an important ingredient that I need to use. So this is the so-called method of characteristic. I'll describe quickly to you. And um, so I need to consider, this method to give a local existence of smooth solutions to a Hamilton-Jacobi equation. So the equation looks like this. I have a Cauchy problem. So I have a fixed given initial data ux0 equals to u0x, and I have ut plus h of x du equal to 0. Um, then the theorem says that if I'm in the class of initial data that u naught with C2 norm less than equal to C, then I would be able to solve it locally from the time minus delta to delta locally, and moreover u is C2. Okay, there. So it's a local result. And I'll tell you a little bit about this one here. And here I'm saying that I'm sort of like literally correct but not absolutely correct. I mean, if I want to be more precise, I should have said that for x, for h, the more correct one is that for hr greater than 0 there exists delta r greater than 0, such that we can solve the problem locally in time, and you have u is C2 of br cross with the minus delta to delta. Okay, so I can only solve it in a compact set, whatever, for a fixed interval of time. So I would say that this is a local existent result and I'm using the so-called method of characteristic. This is in Advanced Chapter 3, and it's also being taught, for example, in a sort of very advanced level of undergraduate PDE. But I'll tell you in right away what we are doing here. Okay, so quick description here. Again, here the Hamiltonian H depend on X and P, and u is a function mapping from x uxt, u equals to uxt, mapping from Rn cross R to R is the unknown, and ut is the t derivative, and du is the gradient in x. Okay, and we are trying to solve this equation locally. And so I mean, what we are looking at here is a first order equation, PDE. So it's of this form: ut plus h of x du xt equals to 0 in Rn cross with, again, minus delta to delta for delta to be chosen, and then we have ux0 is u0x in on Rn, and here I'm given the fact that the C2 norm of u0. So here that u0 and C2 norm is always bounded by C. Okay. So how do we solve by using the method of characteristic? I can tell you very quickly. So this is time, this is Rn. So by method of characteristic is that you are given a point uh, x, and you're trying to find a curve crossing through x or x tilde. Uh, so find a curve xt crossing through x naught, crossing through x naught 0. Find the curves in a nice way so that when you plug into your PD, you can solve it, and that's the deal. Okay, and it turns out that a neat choice of xt t is as follows. Okay, so I'm gonna define pt to be the gradient in x of xtt. So this goes exactly like what we talked about earlier. So this is the gradient, and zt is gonna be the value of uxtt. Then a neat choice of x is gonna I'm choosing x dot of t or x prime of t to be nothing but dph of xt pt, and p prime of t or p dot of t is nothing. Did I use, maybe I used dot, so let me try to be consistent. P dot of t is nothing but minus dx of h of xt pt. Okay, so it's a neat choice. You choose it, and it turns out that this is exactly our Hamiltonian system, nothing more. Okay, so exactly our Hamiltonian system, and with given initial data x0 is x naught, right? Because you're starting at x naught. That's nothing new. And p naught is what? P naught is du of x, du naught of x naught, because it's the gradient of the initial data at x naught. So that's what you're trying to plug in, and you have characteristic curves. You're given any point, let's say that z naught here, then your characteristic or projected characteristic can look like this, depending on the location you type. Why not? And it can go like that. Okay. Um, so that's nice, and it gives you a way to compute the value of u along the characteristic. And if you compute, you see that z dot of t is, by chain rule, this is ut of xt plus du xt t dot with x dot of t, and you use the equations. Ut is what is minus of h of xt pt, right? Because ut plus h x du equal to 0, and du is p, x dot is dp. Okay, so you have the Hamiltonian systems like that, and with the z dot t given like that. So if you can solve the Hamiltonian system, then you can solve along the characteristic, and from there you can find z dot of t, and you can solve for the value, and that's exactly the method of characteristic. Okay, so let me finish it now that I just finished describing to you the method of characteristic. So what's the big deal here? Why can we only solve it locally? So so note, we can only do this locally as x t can cross each other. So you can see that in the picture I drew here, the two characteristic, or so-called two projected characteristic, can cross each other, and if they cross each other, then we things might go wrong, and we might have discontinuity of the gradient and stuff like that. So we would need to use certain techniques called implicit function theorem or inverse function theorem, depending on the setting. It tells us that, okay, if we go for short time, for short enough time from minus delta to delta, then the characteristic don't cross each other, and from there we can, we can see that we can solve the problem locally, and that's it. Okay, so for short time from minus delta to delta characteristic, but we have to be very careful, don't cross. So we have a local theory for solution, and that's exactly what I meant up here. So let me come up here. So you see that for each of the r, we can find a little delta r, so that we can still find a solution for short enough amount of time from minus delta to delta. And the great thing is that this is true for any u naught with the C2 norm less than or equal to C. So delta clearly depend on C here, and this is the key point. And from this local theory, we can go on and gonna prove the big theorem next time. I hope that I can finish it in one lecture. We see, and from that, big theorem, we have a complete theory. But my last point to you is that this is by no means easy, right? We have been building up lots of things. Proving existence solution was not easy. Now, proving regularity of solution, we need to quote this big theorem. In fact, this is a whole chapter, on characteristic method. And from there, we're gonna build things up and then prove the whole thing. Okay, I guess that I can stop now. Do you have questions for me? Any quick questions or long questions or whatever?
Can I ask a quick question?
Sure.
Yeah, so sorry, this may go back to the remark after conservation of energy. So I was wondering why I think it's dxh and dph is Lipschitz.
They're Lipschitz because if P is bounded, right? They are not global Lipschitz in P.
I think it's like yeah, can you scroll down a little bit? Yeah,
Yeah. So
yeah, it says as dxh and dph is in Lipschitz of Rn cross the ball.
oh, that's in the assumption.
I thought that's assumption only for L.
Yeah, but for L you can have it for H.
Okay. And also it's in both X and P.
Yes. So in X in the whole Rn. Again, I mean, what I care really here is actually, you have H is CK. So if you are in a compact set in P, that's not a problem, right? So the key thing of what we are proving here is that what we are proving here is that P is bounded. So P stays in a compact set and X is in the whole Rn, and there I need to put assumptions. I need to put that, uh, like dx of H and dp of H are Lipschitz, in the whole Rn in X. And this is sort of coming from the L, right? Because remember that the Lagrange transform, it keeps the property, nicely between H and L.
Okay, I see.
Yeah. But the key point is really that, yeah, once you have peace bound, that's good. But that's a very important question.
Okay, I see. Thank you very much.
You're welcome. Any other concerns or questions you have for me? And sometimes you can see that I'm starting to be a little bit hand wavy here, because the amount of technicalities is really a lot. So sometimes I'm trying to make a sort of a big pictures for us to see. If sometimes that you can see that if you need to add a little bit more assumptions to make it work, you can add that. That's not an issue. And of course we have to be careful. And you see, that's why I added the assumption that I need Lipschitz conditions in the whole Rn. Okay. Any other concern from me? All right. So if not, then have a great weekend. Um, Happy Lunar New Year to those of you who celebrate it, and also that we're gonna try to prove the whole result next time. I'll need to see. It's just really a long proof, but hopefully that I can make it work. And again, ignore the details. If there are certain things that bother you, surely you should check it. But overall, uh, you know to follow the flow of the course, you should just keep the key points in your mind. I'll try to remind you all the technicalities that are needed in every important proofs, uh, in all important proofs that we're going to face. I mean, hopefully that I remember that. Okay. Right. Other than that, and thank you and have a great weekend. See you on Monday.
Thank you.
Bye. Thank you.